Hello, I am Brandon, and this is my Lab 5 Faraday's Law lab. Our goal in this lab is to relate time-varying magnetic field to a Curly electric field, whose path integral around a closed path is not zero, but provides an EMF that can drive a current. The induced current, which is driven by the tube of aluminum foil, should produce a magnetic field that exerts a force on the external magnetic field, which is sourced from the falling bar magnet. After collecting data, I had to create a computational model to represent the falling magnet. The principles used in this lab include Faraday's law in relation to the Biot-Savart law and Newton's second law. I also had to derive equations for current that exert forces on the external magnetic field. For this experiment, I only had to find the time taken for the magnet to fall, and that was found to be 1.5 to 2 seconds between my various trials, and it averaged to be around 1.8 seconds. Then I had to derive a computational model and plot the motion of the magnet and compare the two. For the first part of the code, I just had to plug in initial values. So the length of the tube, which I found to be 0.3048 meters, and the width of the foil, which is 0.05 meters, and the inner radius of the tube, which was 0.03 meters. The next part of the code is for the magnetic field of the bar magnet. The equations and code that I've used are shown below. For the third part of the code, I had to calculate the magnetic flux through each ring due to the falling magnet, and the equation and the code I used is shown below. For the fourth part, I had to find the current in the ring and the gravitational force. And for the last part, I had to find the net force, which was just the magnetic force plus the gravitational force, and I had to graph the velocity and position. This is what the final code looked like. The first and the last parts of the graph are much steeper in their changes in velocity because it is before and after the magnet falls through the tube, and therefore the only forces affecting that are gravity, but the middle of the graph is the force of gravity affecting it plus the magnetic field. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So the lower the resistivity, the longer it takes to fall through. When it is zero, the magnet won't fall through. And I actually tested it with the resistivity at 1 power of 10 lower. So as seen in the code results in the right, you can see that it took 18.6 seconds instead of 1.8 seconds. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? The induced current from the foil would be lower, and therefore there would be a smaller magnetic field on the system. This, in turn, increases the resistivity, and by the same logic as the last question, this would make the magnet fall faster. Overall, this lab helped me better understand the relationship between induced magnetic fields, flux, current, and magnetic forces. Thanks for watching.